maybe an alternate is in order. So I've heard the words tedious, painful, bewildering, and et cetera, time consuming. So I've always had a difficult time in drawing people into the conversation. It's a very important conversation, of course, but I thought maybe, needed to put on our thinking caps and say, is there a better way to do this? And so, sorry, it looks like I'm missing a slide here. Somewhere in there is supposed to be a thing like, okay, oh yeah, that's right. Okay, and I'm assuming most people here understand the classic FMEA. Jared, is that a reasonable assumption?
I myself am, and I would assume most folks on here are. Not sure everyone's exposure level and expertise as practitioners in generating FMEAs, but I think at least hopefully most are in terminology. But as it is a pretty short list of individuals on here, feel free to unmute and say if you are an experienced practitioner of FMEA or new to the concept.
It's Jean. I'm familiar with it.
I'd answer by, do you want to know how many hours we did it today?
Okay. All right. Well, I won't inflict any pain on anybody then by going over all the details of classic FMEA. Sounds like everybody's familiar with it. I've got an example up on the screen now. This is when I use the term classic FMEA. This is what I mean. It's a thing that came from the AIAG originally, and okay, so everybody's aware of this whole sort of breakdown structure and looking for some rankings in terms of severity and likelihood of occurrence and detectability, calculating scores and the like. So, a little blow up. Yeah, this is typical, process step and some sub steps and events, and you drill down in many levels, and it's really a really thorough method. And for really high risk applications like aerospace or the automotive industry, it seems to work very well. But it's not really a one size fits all affair. So yeah, here's a slide that I got from somebody a few months back, and it's really very detailed, and it really is in fact too detailed for a lot of applications. So we need like a FMEA light, if you will, and that's kind of what we're after. And another thing, common feedback I've gotten from people about FMEA is that the scale is kind of hard to learn, hard to memorize. It's really very detailed, and people have to keep looking back and forth at the scale. So maybe some simplification of the calculations might be in order as well. So yeah, this size, these spreadsheets tend to get really large, and some people have some difficulty in interpreting the RPN score, the calculated score, and most importantly, really not much enthusiasm to participate. It's like pulling teeth. So what do we do about it? That's, I guess, the real question. Okay, fine, we understand the issues, the limitations. What do we do about it? Well, there's this known lean principle: make it simple and make it visual, and that's kind of what we did. This is going back over the course of my last two employers. Had some false starts with this whole thing, had some, obstacles got in the way, and eventually we developed what we thought was a reasonable, simple visual method. So our approach was then really easy. We have three questions, so we'd write the three questions up on the board, and we would address them one at a time. One of the things we would do first would answer the question, what has gone wrong? What has already gone wrong? So we talk to operators, we talk to supply chain people, we talk to a lot of folks and say, oh, hey, when it comes to fill in the blank, this work cell or this warehouse, what has gone wrong in the past that we should be aware of? Then the second question is, what can go wrong? Something that hasn't yet gone wrong, but that could go wrong and that would have some consequences attached to it. And then third question, what will we do about it? So that was kind of the basic structure of this whole visual approach. We go through the answer to those three questions, and a lot of times you end up looping back and it's not all that sequential, but that was really what we were after, to answer those three questions in as simple and visual form as humanly possible. So here's some applications. I've had personal experience with all these applications, and the one that I'm really most proud of, most satisfied with, is the use of FMEA and a visual FMEA approach to address safety risks. And got a nice picture here. You could have a field day with FMEA for these two misguided fellows. And all kidding aside, we would take a work cell and look at it strictly from a safety standpoint rather than from a process standpoint or something along those lines. So just, then the classic typical approach to a new design, warehouse, offices, measurement systems. I have a little bit of measurement systems FMEA content in the second half of this presentation. So you'll see some of that. And then of course, the most classic is to try to look at processes and try to understand the risks associated with those processes. So wide range of applications, and really fits quite well with all of the above and any other things you can think of. If you're looking to analyze and smoke out risk and do something about it before the consequences hit you, this may be an interesting methodology for you. Right, so here's the tactics. The best thing to do, of course, the statement of the obvious, is to do these things at the workplace. So for PFMEA, go out on the shop floor and assuming you have reasonable noise levels, talk to people, write things down, rather than do them in a conference room. And that's maybe one of the other things about classic FMEA. It's typically done in a conference room, and the conference rooms get stuffy, and it takes a long time and people want to stretch their legs. So one of the tactics is to do the work at the work site, in a warehouse, an office, etc. But we've also had good luck where we couldn't work out on, say, a shop floor or something because there's too much truck traffic or there's not enough space. We would take a video and use the video to do this FMEA. That's the visual part. We use photographs. I got an example of that in the next couple of slides. Technical drawings for DFMEA, prototypes. We would take things that somebody made on a 3D printer, and we would look at it and pass it around the room and say, okay, what could go wrong with this thing, and what has already gone wrong with it, and what can we do about it? And then, of course, other things like layout drawings you can use, but definitely a visual rather than spreadsheet sort of text approach, tactically speaking. And it, again, has worked really quite well on a number of occasions. So here's an example of one of our early on visual approaches to FMEA. So we used the standard severity and occurrence and detectability indices, but instead of multiplying them together, and some people complain about that, multiplying them together doesn't provide any kind of weighting to the severity score. So we said, okay, well, let's try this. We'll assign a severity to the hundredths position, likelihood of occurrence of tens, detectability is 1. Kind of stumbling forward with this, and we figured, okay, let's use a scale of 1 to 5. So what we did is we got this photograph. This is a picture of a payoff rack in a rope making factory. So it's got polymeric fiber. It's being fed into a twisting machine, and we wanted to look at that process from a process standpoint, from a PFMEA standpoint. We had done a separate one for safety, and we had then gone on to do one for the process itself. So we would put all the name, rank, serial number as typical, and we would then mark, using these little circles here, different places of concern, visually speaking. So, okay, we could get a bad winding of the fiber package from our supplier. So there's a little 1 there, and it cross-references to this idea. So, and then the potential effect and cause, we could have poor payoff of the fiber, leading to breakage, leading to all kinds of trouble. So we would then, in a group, and I would say always 100% of the time doing process FMEAs with operator involvement, and in fact, as our operators as internal customers. More on that later. So we would get these scores in a group environment. We get severity, likelihood of occurrence, and we would then calculate the SOD score rather than the RPN score. So it was 200 plus 20 plus 1. And then, potential problem number 2, wrong fiber selected by the operator. Here are the consequences and higher severity. And keep in mind, this is a scale of 1 to 5. So when you have a 4 or a 3, that's getting a point where you're kind of getting a little nervous and twitchy. So we would then identify that in terms of its SOD score and onward and so on and so forth. And then we made this, completely arbitrary decision. We're going to take action on everything over 300. Like I said, fully arbitrary, but it was considered kind of a starting place for us. So we would then say, okay, for item number 2, here are current controls. We have some systematic placement of pallets and operator knowledge and different cardboard tube colors for different types of fiber. And, we then made some improvements. We kind of systemized things a little bit better. We asked the question, hey, you who lives in this work cell 8 hours a day, what do you think? And we basically just took action on what the operator wanted to do. So we had some risk abatement. We listened to the operator, we made things crystal clear for them. And in the end, we saw this decrease from 423 to 412. So we had good results. This is what we thought was a real improvement. But when other people looked at it and say, geez, you got a pretty small change in your score. It's like, okay, well, point taken. We got it, 423 to 412. Yeah. What's next? So we tried this and it seemed to work pretty well, but there was still some bugs in it. So we then went ahead and tried something else, silly us. And this time, instead of using a scale of 1 to 5, we use a scale of 1 to 10. So, okay, let's make the numbers bigger. Maybe something better will happen. Maybe things will be more interesting. And so there's a little bit different format here, but the same basic thing. We have a problem. This is a dryer. This is a rope dryer. There's a rope coming in and it goes over a bunch of rollers and it dries the rope because there's some aqueous coatings put on it. We said, okay, something could go wrong here, something can go wrong here, rope abrasions, snags, etc. Assign some scores like we did before and did the SOD approach, 100s plus 10s plus 1s. And okay, we could see some improvements. The high score of 822, we reduced to 812, 623 reduced to 611. Good results, but still kind of a small change in scores and kind of scratching our head. How do we get more leverage to the likelihood of occurrence and detectability scores? And so we again tried something else. And we then agreed in most cases the severity is the severity. It is what it is, right? How can you lessen the severity of something? It was kind of our thought process. And maybe there are some places where, if you have a severity score of 8, you can reduce it to 6. But in the industries I've been in, the severity is severity. If fiber breaks, it breaks, and the consequences are the consequences. So we said, okay, let's fix the severity score. Let's not even think about trying to change that. And then let's change our strategy. And by the way, this is the MSA I'll be telling you about a little bit later. We'll see this slide a little bit later on the MSA front. What we did here is a visual process FMEA for a measuring system. So here's what we did. We went through this measuring system critically, and we found, severities and likelihood of occurrence and detectability. And all we did to get the score was to multiply the likelihood of occurrence times detectability. Didn't even include the severity component in our score. So we had scores 4, 9, 9, 15, and 10. We made some real improvements, wiring labels, and we ran an MSA. Like I said earlier, we're going to be looking at this. Label things more clearly, secure things better, etc. And now all of a sudden we can see our O times D scores drop dramatically. And so not only were we happy with that, but when we showed it to other people, they were happy with it too. So we have some operators we're working with. They show it to their supervisors. Supervisors are happy. Hey, we went from 4, 9, 9, 15, and 10 down to 1, 6, 8. Great, that's wonderful. That's real progress. So a lot of it has to do with presenting the results and convincing others that this is a really good method maybe to use elsewhere. So we put all of the weight on occurrence and detectability. Our focus was on severity. When we were looking at this, we said, okay, let's tackle the really high risk ones first, the fives, and let's make sure, notice it, 535, 525, you know, those were the ones. So we really drilled down on likelihood and detectability and the like. So it's a different approach. It's visual. Sometimes we would use a video instead of a photograph. Sometimes we use a prototype instead of a photograph. But one way or another, we had some visual rather than a spreadsheet. All right. So bottom line is, and yeah, by the way, that's method A, B, and C, sort of in time sequence. And our best results clearly were with method C. It wasn't perfect, but it was visual. It was really easy to follow, which was one of our main goals. And the score provided a real indication of progress made. We weren't spinning the numbers or anything like that. We were just trying to make it more presentable, to get the right weights in the right places, so that we would get some benefit from all of these exercises. So some special handling. Maybe some of you have seen this photograph. This is used by safety managers all over the world, most likely. But if we were doing a P-FMEA and we identified a safety risk, there's a special handling time. We dropped what we were doing and we went out and we took care of it. Said, oh, we found, okay, this possible problem may exist. Maybe people aren't aware of it, and we'd gather around in the work cell and the like. So, you know, safety, of course, goes without saying, comes first. So as we were going through process or warehouse or office FMEAs from a process standpoint, any safety risks were addressed immediately without further delay. So a little practical advice. Yeah, for the PFMEA, you know, start by asking operators what's bugging them today. That's a great approach. I've had, not only with FMEA, but just about everything I've ever done as a process and a quality engineer, that approach just, for me, is absolute magic. You, instead of going to the work cell and say, hey, we're gonna do a risk analysis, you ask the operators, you know, hey folks, what's bugging you today? I don't like the way this material flows or something like that. Okay, you can then turn that into an opportunity to make your PFMEA, which is what you want to do, make it something that you're doing for the operators. Treat them as an internal customer. That would be, in fact, my main advice for everyone that wants to try this approach, is to make it about somebody else that's working in the cell where the actual work is taking place. Then they take ownership. Then you're serving them as a customer, an internal customer, and benefiting your company along the way. And then for safety FMEAs, same drill. Start by asking operators, you got any safety concerns? Just ask them out of the blue. Oh yeah, you know, we stacking these pallets too high and I'm thinking maybe something's going to fall on my head. Especially in the Pacific Northwest, we have earthquakes. So, you know, people, you know, a little bit concerned about that kind of thing. So all kidding aside, start by seeking, again, operator input, and then make it about them. So office measurement systems, make it about those folks, the frontline workers that work in the work cell. And some benefits, maybe some statements of the obvious, but worth saying probably. Better participation. It was pretty straightforward. We used to have a lot of fun with these in some cases. And I never had much fun in a classic FMEA. I always found it to be one of those descriptive adjectives that's on the list I showed earlier. But yeah, better participation, less stress. People, you know, enjoyed it actually in some cases. We got great results. And by having some success and showing people, folks were then more likely to use it elsewhere in other areas, other people. All right, to recap, it's not a perfect method, but there is in my opinion, very clearly an appeal to a visual approach. It is, again, this is my opinion, based on my experience, more collaborative than classic FMEA done with spreadsheets up on a projector in a conference room. We didn't need a legend. 1 to 5 people could handle. We say, okay, 1 to 5, you know, people seem to have the ability to handle that scale and to rank things on that scale much more easily than 1 to 10, where maybe they would need some kind of description. So again, we want to keep it simple. And so we simplified the calculations, O times D, that's it. And I believe that that method is usable across a broad range of applications. And I think that's all I've got to say on the matter. Yeah. So any questions or comments? Anybody think this would be a complete disaster in their place, in their employer's operation?
No, I really appreciated the focus on safety. I've never really, in my previous experiences, seen it applied to safety, but I can absolutely see its benefit as a tool, and particularly with the visual aspect to really drive focus on the work cell. So I greatly appreciate that that centered approach there on safety.
Yeah, Roger that. We kind of stumbled into that whole thing. We had some people talking, and then somebody came up with the idea. In fact, can't be 100% sure, but I think it was a production operator said, hey, why don't we just look at this area from a safety standpoint and worry about the process later. So it was kind of a spin-off. We stumbled into it, and yeah, it seems to have good traction and real application. Any other comments?
This is Bob Funk. I also found it interesting. Mill Standard 1629 was always a 4 levels all it had. And it was a heck of a lot easier to a lot of times identify quickly, even with just that 4 level. And they did it for all 3 factors.
That's
Mill
that really
16.
A lot. Sorry, that was Mill 1629.
Yes.
Okay.
I mean, and the only thing they did stupid was it was always in sync with the safety hazard analysis one, and then they reversed the two. So you always want to make sure if you have a separate one for safety, you need to keep them in sync. But the other thing I liked is your comment about the drawing brought back memories to me where in the beginning on doing a DFMEA, that was the first thing we do is you'd pull out the drawing, you'd start looking at if it was a schematic for the wiring, you would basically be looking at, okay, what's doing what? You'd be marking up the drawing with about 80% of what you were going to end up transferring to the DFMEA separately, and you'd be talking right over the board, back and forth and figuring out what your risks were that were there immediately, and then going there rather than as tedious. I thought that was kind of interesting, particularly when you're doing early FMEA.
And so when you were looking at the product drawing and all that, making your notations, if I understand you correctly, you thought you got like most of the information you needed to fill out the table. Is that right?
You got a whole lot of it because you started looking and see, well, wait, if that shaft's now, so I need to put a key characteristic on this so I can hold it there, because if that shaft comes loose, ouch, I got a problem. Yeah. So you were marking, and you were even doing that at the same time. You were marking your key characteristics right after you saw what the issue was.
Yeah.
Where they made sense.
Yeah, in our environment, we figured, hey, if we can get 70-80% of the way there just with the drawing, let's do that. Maybe spend a little bit extra time on it, see if we can get the 85% and leave it at that. Yeah, so, and you can do that in an unregulated environment or where you don't have some expectations. So yeah, so you guys were the pioneers then, not us.
No, this was just when you did an early FMEA. You ended up having to bring it across to more of the rest, but when you were just looking at it, you barely even had concept drawings, or you barely had, you almost never had a part. You could do a lot of that markup and then see it and see, okay, how's this thing going to break? And what do we already see as a problem?
Yeah, cool stuff. Yeah, visual is good. Visual is good. It's, drawings, great place to start for a design FMEA. Agreed. Other comments?
I would actually say that the picture, the idea of having the picture, especially with so much virtual, has been super helpful, because even the drawings are really great when you're in a room and can spread out and look at it. But being able to even have a picture is very helpful. In fact, ones that we did recently, we ended up having someone go take a bunch of pictures of some things so we could bring in and point to everything and discuss how things actually went together and stuff. I think that visual aspect is very, very critical.
Yeah, agreed. Hard to describe things in words and put those words into a little box. That's maybe why people consider the whole classic approach to be a little bit tedious. You know, maybe one person's thinking one thing, one other person's thinking something completely different, but when you got a picture, all is clear.
And the same thing goes on the CAD. As you've got 3D CAD, if you can move it around, if you got the poor man's CAD that almost any of the places can use, you can move the piece around you quickly. You're able to see a lot of stuff too that you actually couldn't do in person with a real part. Always quite the same, which is kind of weird.
Yeah, that's one we never did.
A 3D PDF. Yep.
Yeah. That's an interesting point. Yeah, use a CAD system, you know, a little bit maybe more dynamic FMEA, you know, so you identify
you flip the
things.
part around.
Yeah, and then start making some changes on the fly. That's a really, wow. We'll be standing by for your presentation on that thought. That's the next logical step, isn't it? CAD FMEA. Yeah, excellent.
Well,
Excellent.
and I think
Great thought.
I think I can definitely say that the CAD really helps too, because you can when you're doing it in CAD, like if you start talking about serviceability issues and you want to know if it has enough clearance for a certain type of wrench, you can actually take those measurements and stuff right in there. I've done that in some of my previous jobs before, where we sort of loaded up a wrench and, you know, tried to see what would fit and things like that. You can do that live.
Interesting stuff. Okay. Yeah, Jared, just a quick side note. Do we have any, you know, time constraints here? Is expected to end at a certain time?
No, it's a pretty open format, and
Okay.
definitely the open dialogue is appreciated.
Yeah, absolutely agreed. Yeah, that's the best part. So it's about 10 after 4 my time. So yeah, if there's any other comments or questions on this, if not, then I can go on to the second subject. Okay, we'll move on to the next one: how to convert opinion to continuous data for $10. And by the way, I have to confess early on that it actually cost us a little bit more than $10, but I'll explain that a little bit later. So this is based on a paper that a gal by the name of Lisa Martin and I published and presented at the 2018 ASQ World Conference in Seattle. So I've taken that presentation, distilled it down for this forum. All right, it's about the whole thing. You know, if I want to convert, you know, opinion, I want to convert opinions so that I can understand customers. That's really kind of the whole idea here. We want to understand customers, and we want to be able to produce products for customers that they'll like. And sometimes that's a real challenge. And this, I'm gonna do this part of the presentation in this case study format, and it's about the development of a new arborist rope. Arborists being these really brave people that climb trees and trim branches and do all the tree doctoring stuff and the like, and it's really dangerous. And arborists are really, really particular about their ropes. Their lives depend on it. They're in contact with a rope all of the time they're off the ground. And their opinion of ropes is in fact really very subjective. So we've got a kind of an elusive voice of the customer, if you will, in it. And so we asked ourselves this question, you know, how do we turn the dials and pull the levers in our process, all of our X's, all of our process factors? How do we control those and try to model it to something that matters to an arborist? And well, as it turns out, there's this thing that arborists, at least in the Pacific Northwest, refer to as the hand of the rope. I think that term's also used like in the fabric industry. You know, how does it feel in the hands? Very subjective, very vague. But we had a new competitor prize when I was working for a company that made ropes, and we not only made ropes for super tankers and mooring and the like, but we also made arborist ropes. And there was a new competitive product that was a threat to us. The arborist liked the hand of the rope. I was thinking, oh my God, what on earth is, how are we going to measure this thing that is, at least at first glance, unmeasurable? So rope hand is kind of tactical flexibility of the rope, you know, way it feels, it's kind of sort of. The good news is that it was consistently subjective. So if we had a rope sample and we had an arborist or some subject matter expert evaluate the rope, we were getting pretty consistent. Yeah, this is good, and this is really good, and this is horrible. And those opinions were at least consistent. So subjective and consistent, maybe you can handle. Subjective and inconsistent, maybe there's no answer. But we were getting sort of a common feedback. The problem is we wanted to run a designed experiment. We wanted to run a DOE. We wanted to be able to run rope under different conditions in our processes, and then get our response, to create our predictive model. And it's really hard to do that with things like, well, this is good, or this is not good, this is acceptable, this is not acceptable. In the DOE world, you really need a continuous response. So there was no direct test. There was no, hand-o-meter where we could put a rope in and it would say, okay, this has got good hand, or this has got, got this score or that score. So there's no direct test. It was a huge problem for us. We had to put on our thinking caps. What are we going to do? So this is kind of the classic approach to understanding customers. We got our typical, data type structure. An opinion, like rope hand, would be typically converted to some kind of ordinal scale, a Likert scale or something like that. You might go out with a rope and say, okay, for this rope, please check one of the following 5 boxes. I like the hand of this rope. Strongly disagree, et cetera, and give you an ordinal response. But using ordinal data in experiment as an experimental response requires a lot of assumptions and a lot of compromises, and we were really uncomfortable with that approach because this was a competitive threat. This was money disappearing from the company's bank account. So we were really highly motivated to come up with a different solution, and it required some thinking and measurement systems analysis, et cetera. It was kind of a long slog before we got to the point where we could, in fact, run a designed experiment the way we wanted to. So I'll give you a little bit of background on rope making. Here's a little rope 101, just to put all of this into some perspective. So you start with fiber. We saw that in the V-FMEA thing sitting up on a rack, but it's a spool of fiber. It's typically, for high performance ropes, HMPE fiber, and for arborist ropes could be a combination of polyester or nylon, and it goes through a twister. So you take a whole bunch of these and you run it through a twister and you get what's called a strand. So taking the fiber, which is essentially parallel, and we then twist it and gang a whole bunch of them together and put it onto this thing called a braider bobbin. So got this thing. We take a whole bunch of these things that are packaged on the braider bobbin, thing called a strand, and we put it on a braider, where the braider has this rotating turntable that literally braids the rope, or braids the strands into a finished rope. So that's kind of the basic process, and we're able to control lots of things along the way. That's the good news. I think I have that in the next slide. Yeah, so it's a complex process, which can be bad because, okay, you got a lot of stuff, but the reality is we had control over a lot of things: fiber types, twist levels, braiding levels, the types of coating we put on, lots of different things. Can we put the fiber in different layers? Can we put one fiber in the center of a bundle and put a different type on the outside of the bundle? Lots and lots of factors. So we had a lot of things to play around with. Our problem, so here we go, we got this equipment, X1, X2, X3, and it goes through a braider or a twister and then a braider, and this is kind of a conceptual drawing, but we had no way to measure. Just before this rope got spooled up on a spool, we had no way of measuring what we really wanted to measure, which was the hand of the rope. There's no gauge, couldn't find one. So the solution, of course, was to run some designed experiments and then find a way to convert opinion into a continuous value for rope hand. Another arborist up there doing really dangerous work and fully reliant on their ropes. So their opinion was important. If you don't have a rope that feels right, you're not going to sell it to these folks. So the solution, this is where the true confession comes in. The solution is a $10 tape measure. As it turned out, we started with a $10 tape measure. It had only feet and inches, and that was a complete disaster. So if I were to provide some friendly advice, use a tape that has only a metric scale on it. And they're hard to find. There's one Tajima model number such and such has only metrics rather than what you typically find in the US, which is feet on one side, feet on the top of the scale, and metrics on the bottom of the scale. And that can cause a lot of confusion. So as it turned out, I spent $35 and had this Tajima H1550 MW imported from Japan, and it worked a charm. And that's a really great one. You can get them on Amazon or eBay for about 30, 35 bucks. So if you're going to go down this rope, I strongly recommend you get one of these and not use, definitely don't use fractional feet and inches. Oh my God, you have everybody spinning around like a propeller trying to do all the arithmetic. So there was the solution, and here's what we did. Here's the setup. There's my colleague, former colleague, Lisa Martin. Her and I did this paper at the ASQ World Conference, and she is a subject matter expert. She's not an arborist, but she's been making rope and talking to arborists for about 30 years. So she's a real subject matter expert. She worked for the company. So what we did is we found this nice flat surface, and we took our tape measure. This is one of the early trials. You can tell it's not my Tajima tape measure, but this is one of the early trials. And we secure the scale down, and then Lisa would take ropes made under some different conditions, because when we run an MSA, which is where this is heading, we run an MSA, we want to sort of test the limits. We want some that are going to be on one end of the scale, some on the other end of the scale. So she would take and evaluate the rope like she's doing here, and she would then put it on the scale. So we were using, I think, 300 centimeters of the scale. And so if two ropes were really good and really similar, they would be set somewhere like this to the right side of the scale. If it was really poor, it would be set way over here to the left side of the scale. So this is where you get the continuous part of the scale. So we're not just putting them in order. This one's better than this one's better than this. It's not an ordinal measurement, but because you can leave these gaps between, say, this one, which is sort of looks like it's sort of medium of the road in terms of its hand. There it is, but nowhere near as good as these two. So this is the magic. This is what got us converted from this sort of opinion or good hand versus it's acceptable, it's not acceptable, it's good, better, best. We got out of that world and we got into the continuous scale right here. So she would then evaluate all the ropes. We would then write down the numbers on the scale. So the ones with poor hand would have a 0 or 10 or 15 centimeter score. These would be 20 or 30 or 40, I don't know, maybe more than that, maybe 80 or 90 centimeters. These up here would be 2.6 meters or something like that. And we would use that as a continuous score for the rope. And we even had some arborists. This is the plant where Lisa works is actually in your namesake in Lafayette, Louisiana. And there were some arborists, local arborists, and we brought them in and bought them some pizza pies and all of this, and we had some fun, and we had them do the same thing along with us. So we had a variety of subject matter experts, and it was really great. It was really good fun. We met some customers, and the customers came in, we treated them well, and got to know each other. So this kind of setup is the key to it all. And let me explain further. So we start with this visual FMEA approach, and we looked at this from a safety standpoint. So we said, okay, well, not a whole lot safety-wise going on here. We weren't talking about the use of the rope in the field and the possibility of rope breaking. We were just looking at the measurement system, and we gave it kind of a good once-over and said, are there any safety issues here? And we decided, okay, there really aren't any serious safety issues. But we went through the process, and that's the key point. Pretty much everything that we've done project-wise when I worked for this company, we would always do some kind of safety review first, without fail. And then we looked at physical issues, ergonomic issues, and before we even started anything, we were able to make some improvements, we thought, in the measurement system by doing this, sort of risk analysis. What has gone wrong? Somebody said, oh yeah, the tape measure fell off the table. All right, let's do something about it. What could go wrong? Well, it could come loose and fall off the table. Okay, so we figured, okay, it's fine, a good way to secure the thing down. People might interpret the scale incorrectly, and they might think right is bad and left is good. All right, let's put some labels on there saying this side is bad and this side is good. So this is the sort of error-proofing approach that we took as part of this exercise. We looked at ergonomics. Is the table at the right height? Is the lighting good? All of that kind of thing. We then proceeded to a measurement systems analysis. So we took 7 parts that represented kind of the broad scale of things, and then we had 3 subject matter experts, and we had them do it blindly 3 times. So we had the rope marked discreetly. They all looked the same. They're all the same color, same length, and attached. The ends were, secured the same way. So we made the parts look as similar as possible. We used a 300 centimeter, 3 meter scale, and we asked ourselves a question. Do we have evidence from our MSA to convince ourselves that this data is good enough to run as a design experiment? Because a design experiment was a little bit pricey, making the ropes, setting up to run under different conditions, different gearing, and all of that. There was some serious cost involved. So we want to make sure our measurements were good before we embarked in the in making samples under different conditions. So this is typical Minitab output, as is their variability chart. So we had subject matter expert 1, subject matter expert 2, subject matter expert 3, and in this case we had these 7 ropes, 1 through 7 for each of the experts. And here's the 3 measurements: so gray dot, and gray dot. The dark dot being the average. So this is kind of a visual signal to noise ratio thing that Minitab does really well. And I really like this this variability chart they have built, and I use it all the time. And this is one of the things. This is my first look at my MSA data. I always look at the visual, and then we can drill down and we can look at gauge R&R. So for those of you who use Minitab, you might look at something like this and we say, okay, we've got some. And by the way, all of this data is all synthesized. It's all, I've made some data up for, keep things confidential and all that. So this is not the real data from the rope analysis. I don't work for the company anymore. So just so it's clear. So making things up maybe don't make really a lot of sense, but we could see, okay, we've got some repeatability issues, but pretty reasonable signal coming through nonetheless. For those of you who use JUMP, you look at this, and you can go right to the bottom line. This would be considered in the EMP world rather than the gauge R&R world a second-class measurement system, which according to Donald Wheeler's is useful for a lot of cases. So we would see that same sort of signal to noise ratio here in Donald Wheeler's intra-class correlation coefficient. Now, I like just saying the signal, the size of the signal, a little bit easier to say. But anyway, so we got this baseline. So our first go after our FMEAs, all of that, we ran an MSA and we had this baseline, and the results were pretty good. But we're thinking, there's some risk involved. So we decided, okay, let's not accept this as it is. Let's do something. Let's make some more improvements. So we revisited our visual FMEAs. We did some more decluttering, and then we stumbled on this idea that if you have these subject matter experts doing the analysis while somebody is watching them, that's really not a very good idea. So term that somebody coined Orwellian bias. Don't have Big Brother watching your people doing your measurements for you. It is never a good idea. So we took some steps and we said, okay, let's run the MSA a little bit differently, see if we can get rid of some of the random response variation that we can actually do something about. We looked at the lighting, room temperature. One of the operators said, it's getting warm in here. Okay, let's do something about it. So we made some improvements, and we ran our MSA again. So this is also simulated data, but we can see very clearly from the variability charts, which is scaled the same, we could see an improvement, better repeatability and the like. In the MSA world, here's the numerical output in Minitab. So okay, we started with 25% noise, now we're down to about 11-12% noise. So we got much better signal to noise ratio here. Really happy about that. And we really did see lots of improvements. And if somebody wanted to unmute, I thought I heard somebody maybe unmute and wanted to ask a question, or no? Okay, false alarm, sorry about that. So this is after we made the improvements. And for the jump folks out there, now instead of a second class, we have a first class system with a signal strength of about 93%. Wow, now that sounds good. You know, you're running a DOE and you've got this much signal coming through. Usually pretty happy with that. So we decided, okay, let's go ahead. Now that we've convinced ourselves all is well with our new response, continuous response, let's go ahead and commit the resources to run the DOE. So here's a kind of a summary. The response was hand, and by the way, we're also measuring some other things like cycle times and other things. We had multiple responses, which are really pretty easy to balance in the, you know, when you run a design of experiments, you get things like the Minitab optimizer or the jump prediction profiler, able to balance things. But for the discussion, we'll say, okay, we want to focus on the hand, and we took an average of 3 expert opinions using that measurement system that we developed. And so there's continuous. We could calculate an average. Hard to calculate an average for an ordinal scale. Some people do that. They'll assign 1, 2, 3, 4, and 5, but it's a little dodgy because it's not really a scale. It's not, you know, from strongly disagree to disagree may not be the same as disagree to neither agree nor disagree. So there's that whole thing about ordinal data has some limitations, and certainly acceptable versus unacceptable. You know, what can you do with that? But we were able to calculate an average, and that was the key. So we had some factors. We actually, full confession here, we actually had to run a screening experiment first. Remember I said lots and lots of factors in our process. So we ran a definitive screening design, which you can then actually reduce. I don't know if anybody here's got experience with definitive screening, but you can actually reduce it to a, you know, some kind of quadratic model, and, you know, just find the factors that are important. But we ended up running an optimal design using these 3 factors that we found were the big. This was the, you know, the Pareto principle. There were a few key factors that were affecting rope hand, and we knew then what they were. So these are our factors. We ran some replicates, so we had to run 21 samples of rope to get our answer. That was a reasonable amount of work and a reasonable cost. So for those of you that use Minitab, this is the Minitab response optimizer. You know, this might be the most useful graphic in the world of process and quality and industrial engineering that we have available to us. This is a visualization, an interactive visualization of our process model. We've created a mathematical model of our process, and this graph visualizes it, so we can play around with X1, X2, X3, and see what the predicted value of rope hand would be. Well, hand would be maximized at X1 of 500, X2 of 62.3, top of this curve. Again, this is all synthesized, and X3 also at the top of this curved shape. So we would get a predicted value of 315 under those conditions. And for those of you that use JUMP, this is what that data would look like in the JUMP prediction profiler. And again, folks, if you wanna tie the voice of the process, or sorry, the voice of the customer into the things you can control in your process, this is the way to do it. There is no better way, because we could say, okay, where is the best possible hand for the rope? And we actually ended up balancing against some other things that were important in the rope as well. But at the end of the day, it worked a charm. And we ended up developing a new rope that was able to compete with the competitive threat. So the underlying model, we had, you know, full quadratic model. We had our main effects, we had our two-way interactions, and we had our quadratic terms, you know, showing us that. And again, I synthesized the data, but there really was some curvature. There were some maximum values for some of the factors. So it was really important to get, you know, a full quadratic model for this challenge. So explain, there's kind of 2 basic approaches you can take to this. I'll call it method A and B. Method A is to use one subject matter at a time, doing it alone. And this is what we used for our design of experiments. We averaged 3 scores. So, and instruct them to group the similar parts, make sure they understand the scale and where to leave the gaps, and make sure there's this proportionate space Is it a little bit better? Okay, make it a little closer. Is it a lot better? Okay, make it further away. That kind of thing's important. And then record the values, reset everything, and then bring in the next SME, sort of a serial approach. The other option is to have two subject matter experts working together in sort of an iterative process. Okay, you feel this one, okay. Okay, I think it should go here. No, I think it ought to go a little, and then they compromise, and that has some value too. You get a little bit of difference. People filter out some of the noise that you might have in your measurements when you have a couple of people working together. But same drill, group the similar parts, and then record the values, reset it, and then bring in maybe two other subject matter experts, or one of the original and one different, to try to get a real good indication on an average basis of what the rope hand really looks like. So here's some more examples. That's the end of the case study, but here's some more examples. I've used it effectively for things like color. So rope color, very hard to measure. You can't put a gauge directly on a rope because of the uneven surface. You have to do it visually. So we would use the center of the scale as our desirable condition rather than the far right or something like that. And lighter ones would go to the left, darker ones would go to the right, and we would have a standard, say this is the color we're trying to match, and get a lot of different people to evaluate some different samples that we maybe made as part of an experimental design. Say, okay, which is the best one? And we could use that data from the scale as an experimental response variable. The fellow over here in this photograph, what he's doing is evaluating the edge quality of some foam orthotic brace inserts. So he had a water jet cutting the edges to form the shape of a human foot. And the edge qualities really weren't very satisfactory. You get like fuzz and all that kind of stuff. And we tried, trimming off the fuzz and weighing it. None of that really worked. But what would work is the scale. So here's a person who really understands water jet cutting of foam. Not an easy thing to do, as it turns out, and he is putting, all the worst part here, the best part here, and grouping things together where results might be similar, and you might have ended up stacking some on top of each other. But how carpet feels underfoot, I've seen it done. That was, in fact, the first time I ever saw this method was in a carpet factory. People just stood on it and said, okay, I like this one, and I like it this much. So surface texture of things, if something that people are going to touch, they want some customer feedback on some tactile properties where they say, oh yeah, this is good, or this is not so good. I don't like the feel of this. You can use this method for characterizing surface texture as well. All right, so coming down to the end, the benefits, statistical leverage. In the world of design of experiments, there's nothing like continuous responses. Anything else is a serious compromise in my experience. So this is the blockbuster application of this approach. Any of you that are running design experiments and trying to design something for a specific customer satisfaction level, this is a great approach. So all of our design of experiments, our continuous improvement work, we got much better paybacks using this method. And or sometimes people just gave up. Hey, we got no way of, the customer opinion is subjective. There's no way to measure it. People would give up. So we found a workaround. And then it demonstrates the benefit to others. Again, just like in the FMEA world, if you can have some successes, through a visual FMEA, be it a safety FMEA, people will start using it elsewhere. And that's what I've found in the past. It's like, hey, I can, we would present our results to a group of people and they say, hey, I can use that. I can use it over here, use it over here. So you get multiple benefits, kind of a, sort of a, snowball effect, and the impact on your company's bottom line can be really quite profound using these, experimental approach with the right response variable. All right, so summarize continuous data. No contest. It's the only way to go. And again, think about your customers as a subject matter expert. We brought in some arborists. That worked great. I loved it. And as a response variable in our DOEs, it was brilliant. All right, that's the end of it. So hopefully that is of some interest to you folks. And see, it's about, honestly, your time is what, about 7:35 now?
Correct. Yep.
Okay, well, hopefully that's not too late for y'all. Sorry about going over the 1 hour, but yeah, any questions or comments on that method?
I thought it's a great method, and yeah, appreciate your honesty there. Switching from the U.S. to standard to metric, and the honesty from $10 to 35. But I think when you do have difficulty in ranking that very subjective data, putting it to a continuous visual like a tape measure is a great idea. So really intriguing solution, and already thinking of ways to apply that in my organization. So
Great. Yeah, you're in the medical devices industry, right?
correct.
Yeah. Yeah, I have a little bit of experience with orthotic braces. So there's polymeric things to treat walking disabilities. It's a class 2 unregulated medical device. It's probably not the same as you, but yeah, the fit, how does a thing fit? How does it feel? Oh, I think it feels good. I think it's to this. I think it's to that. Yeah, all opinion based, and using this method, you can convert your customers' opinion into something really useful. So hopefully you have some application in your business.
This is Bob Funk. I want to give you an overall compliment too. You may not know about this book. You might know about this book, but we brought in Dr. Joseph Motter. He had the book Designing for Quality, which I like to call the fourth grader's guide to DOE, and the best book I've ever seen for teaching anybody DOE. Very simple and basic. And he would describe it the same way, in terms of just bringing it so simple. We had 75 people show up to the guy's class, and he's the same guy who rolled out DOE to Motorola, believe it or not, when they did the Six Sigma. But he was so practical that if they haven't got that book, Designing for Quality, it's amazing. It's the simplicity of what he did with how to do it, and just a lot of the things like you described. I mean, even down to your comment about how to run things the opposite, where he'd talk about a fold over, which was nothing more than, okay, you ran if you don't know what the heck you've got for it, go ahead and run less of them. Now do exactly the opposite and do what they call the fold over. So you've got all
fold over design.
You haven't got, fold over design. And so you don't know what you got. Well, after you did the fold over, now you've got a good chance of having the variable. Now go in and do the real thing, But he was so practical, and I appreciate that you're doing here.
Yeah. Thank you very much. And by the way, that whole fold over approach ended up sort of morphing into the definitive screening design, which is built into both Jump and Minitab. Very, very powerful DOE tool. Yeah.
Oh, absolutely. Yeah, I wondered about that one, but I didn't know the connection.
Yeah, definitive screening is a fold over design. If you unscramble the designs, you'll see, different rows. They're mirror images of the other rows. So if you got -1 in one row, you got +1 in the other. If you got a 0, and then you got a 0 in the other one as well. So there's a whole fold over design. So that whole concept had real legs. And from my standpoint, definitive screening designs are the absolute blockbuster breakthrough of the 25 odd years I've been running experiments. When I saw it for the first time, I almost sat down and cried. I was just so happy to see how useful it was, because you can reduce the model, and then you can start with a screening design and find out what's important, and then you can reduce the model and get a quadratic fit, because it's a 3-level design. It's absolutely brilliant.
Right.
Yeah. Cool. Well, hopefully that was useful. And by the way, it's not really just for design of experiments. It could be used for lots of things. Customer. Just to get a general feel for somebody's opinion on something. Really great to break out that tape measure and just have people put it on a scale. It's almost like a game. People really, they say, hey, this is really cool. It's almost like a game they're playing, and it's hands-on, and people have to move around a little bit. So a lot of kind of a good Swiss Army knife approach. It's useful for a lot of different things. I've presented it as a DOE response variable, but definitely don't think it's not useful for anything else, because it is. All right. Anything else? There's my email address. Anybody, I'm more than glad to help people out in the future. And, if you've got questions on some of the things you've seen here, I'd be more than glad to help you out. I wouldn't expect anything in return, just one enthusiast helping another. So feel free to get in touch anytime. I like talking about the subjects. I like hearing about other applications. I learned a whole bunch of really cool stuff today, so thank you very much. Yeah, keep in touch if you'd like. Not a problem.
Excellent, and greatly appreciate your availability to present to us this evening on these two topics. I definitely learned something tonight, and that's our intent with any of our meetings, is that we hope that our body of members go away with some additional information and some ideas to apply in their industries. So again, greatly appreciate it. And this was recorded and will be up on our site. So for the folks that weren't available to attend, they'll still be able to enjoy all the content that you presented on this evening.
Great. Glad to help.
Does anyone have any other comments or questions before we conclude the meeting for this evening? If not, we'll call it a night and or late afternoon. So for you there, Steve, hopefully you have a wonderful rest of your evening, and for everyone else, thank you for attending, and we will send out, after our section leadership meets, we'll hopefully put together our plan for the fall sessions.
And this is Bob Funk. I don't know how many other people are CREs and CQEs. So if I can get proof of attendance, Gene, I appreciate it again.
Will do. I'll take care of that.
Thank you so much.
Yep, same here, Gene. So,
Who was that? I'm sorry.
this is Jared.
Okay, got it.
Excellent, thank you.
Uh-huh.
All right, Stephen. Well, again, greatly appreciate your time. Excellent presentations. Look forward to hopefully crossing paths with you again in the future. And again, best of luck to you. And again, thank you again for taking your time this evening to present to the Lafayette section of ASQ.
My pleasure. Take care.
You as well.
All right.
Good evening, all.